where you act on a single data item at a time. So you have some machine learning model typically, and you look at one data item and you want to make a decision. That's either streaming, if it's a stream of updates or whatever, or it's what we call stateless model evaluation, if there's a user making some requests, translating to you want to evaluate some machine learning model, right? That's not what Vespa is for. Vespa is for the other case where you want to evaluate some model over lots of data that you also select dynamically on the fly, given the query. So that's what we call big data serving, and it's what Vespa is developed to solve. So what's required to do this? Since you're taking actions in real time, you need really low latency. Typically, latency budgets for Vespa are around 100 milliseconds because it's for end users, and end users get impatient if it takes too long. We need to be able to act on real-time knowledge, so it needs to sustain a high write rate, typically tens of thousands of updates per second per node. It needs to be scalable because there can be lots of queries when they're coming from end users on the internet, and it also needs to handle a large amount of data, obviously. Also because it handles queries directly from end users, this needs to be always available. So we need to be able to recover from hardware failures and so on without needing any human intervention. Just keep running always, kind of like Hadoop. We need, for the same reason, it needs to be evolvable online. So we need to be able to change schemas, the logic of applications, the machine learning models, the hardware, and so on, while we are serving and handling writes with no disruption whatsoever. And because it's part of the larger big data ecosystem, we need it to be integrated with Hadoop for handling writes that originate from Hadoop and so on, and be able to evaluate machine learning models produced by TensorFlow, Caffe, Spark, and so on. So Vespa is an engine that provides these features, plain and simple. Like Hadoop, actually it grew out of the search organization in Yahoo. So when you do web search, you have two problems. One problem is you have lots and lots of data that you want to process really fast, and that's what Hadoop was developed to do. The other problem you have is you need to be able to find subset of that data and evaluate machine learning models over the subset of data while the user is waiting. Because in applications like search and web search, you can't pre-compute an answer to every given query, right? But because there's just too many queries, so you need to do it in real time. And this second problem is what we developed Vespa to do. It was actually started a bit before we started Hadoop, but we haven't been able to open source it until recently because of the complex IP rights around search. But we're finally able to do it late last year, so now it's available to everyone. So what can it do in some more detail? It can do natural language unstructured search over text combined with structured search in structured data, relevance scoring used for both natural language processing, natural language search kind of use cases where we have natural language text relevance features. You can use it for things like recommendation, where you want to use different kinds of machine learning models and so on. And you can plug in machine learning models from things like TensorFlow. You can do organization and aggregation of the matching data on the fly, described as part of your query. As I mentioned, you can do real-time writes while you're doing this. And the clusters are elastic and auto-recovering, so you can add and remove nodes and let nodes die and so on, and the system keeps working, handling all the queries, the writes, and so on. And just redistributes data in the background to maintain the data redundancy that you have configured. It also has a processing logic container, because typically as part of these applications, people want to run their own business logic, so you can deploy that as part of your applications to Vespa. And because these systems can be large, because there's lots of queries and lots of data, they're typically not as large as big Hadoop clusters, but typically up to a couple of hundred nodes. So it's too much work to set up all those nodes manually. So we use managed clusters where Vespa handles setting up the clusters and the nodes and so on for you. So typical use cases are text search, personalization, recommendation, and so on, and also real-time displays where you have lots of data and you want to use that data to compute some kind of display interactively while the user is waiting. We use it out for all the search use cases, obviously, but even more for recommendation and personalization kind of use cases. And one prominent example is the front page of Yahoo, where we have a list of articles that we display when the user is visiting the site that is computed on the fly based on the personalized profile of that user. And that is done by Vespa. And the same thing with the native ads in this stream, also computed by Vespa on the fly using other personal machine learning models using your personal information, and in addition taking things like bid information into account. And every time we display an ad, we update the budget, all the ads for that advertiser on the fly and so on in the system. So in total, a node, we execute a couple of 100,000 queries per second on Vespa. I'll skip this. This is one of the other use cases where we have some nice quotes. I guess the only thing to mention about this is when this company decided to move to Vespa, they spent about a quarter to migrate their recommendation and search, and also build a type ahead search on Vespa. So what's out there that Vespa is similar to? Vespa is most similar, I guess, to Elasticsearch. But the focus on Vespa is on big data serving, so really low latency, large scale, but still being cheap to operate, and machine learning models, while Elasticsearch has more of a focus on analytics, where you typically have somewhat higher latency budget, like a second or a few seconds, and not so much focused on machine learning models and that kind of thing, but more on log ingestion, time series data visualization of that data, and so on. It's also similar to Solr for the natural language text search capabilities. I'll skip the rest. Yeah, this just compares analytics, which is Elasticsearch strength, with what we call big data serving. I'll just go through it very quickly. In big data serving, you have lower latency budget, higher query rates. You need to support random writes, and you need the high availability features I talked about. So Vespa provides that, but the flip side is if you have really massive data sets, like hundreds of billions, trillions of documents, then Elasticsearch can be cheaper than using Vespa. So that's a trade-off. So just quickly, architecture of Vespa. Vespa is a two-tier system where we have a stateless container in Java that handles all incoming queries and writes and so on, and executes the global part of the logic of handling incoming traffic. And then we have what we call content clusters that stores the raw data, executes the distributed part of queries, executes machine learning models, and so on. And this is all C++ because it's optimized to handle all that data efficiently. And we have a third kind of cluster, which is what we call the administration cluster, which sets up and controls these clusters and nodes and processes for you, so you don't need to do that manually as a user. So what the user sees is a more abstracted view of the system, which is what we call an application package, which describes at a high level the clusters you want, the capabilities you want of those clusters and so on, as well as the data schemas, any Java components, machine learn models, and so on all go into that. And then you deploy the application package to Vespa, and Vespa sets up the system for you. If you want to change your application, you just change the application package and deploy it again, and Vespa will carry out the changes for you while live serving queries and writes. So the main point of Vespa is to do computations or lots of data with really low latency. So how do we achieve that? There's three main strategies. The first is parallelization. Incoming queries are sent to all the partition nodes that have data for that query in parallel and evaluated on the subset of the data in parallel. And on each of these nodes, we use multiple cores for every query in parallel, sharing data between the cores and so on as we evaluate. Secondly, we move as much of the execution as possible to the data nodes rather than sending data nodes to some stateless node for execution. That's the same strategy as Hadoop uses, really. So when we evaluate machine learning models and so on, we don't look up the data, send it to a single node and evaluate the models. Instead, when you deploy models, we copy the models and all the data they need and so on to all the partition nodes having data. And then we send the queries to the data nodes and evaluate the models locally over the data and then aggregate the results. And lastly, obviously, this is a search engine, so we use things like reverse indices, posting lists, B-trees, and so on to be able to execute the kind of queries that we want to support quickly. So a large part of the effort on Vespa over the last couple of years have been supporting more advanced machine learning models on Vespa, typically driven by the personalization and recommendation use cases where you want to use things like deep neural nets and so on as your machine learning models. So as part of Vespa, we have a tensor data model and a tensor math language that is supported natively on Vespa and executed on the data nodes or the data. So when you deploy a machine learning model to Vespa, you express it in the Vespa tensor math, and Vespa will execute it for you as part of evaluating queries. So we have a tensor mathematical language with a few operations that can express all the common operations that we see in things like neural nets or other kinds of models, right? So they can all be translated to a combination of the simple operators that we have in Vespa. So that allows you to write machine learning models by hand, either using these high-level functions or the basic low-level functions of Vespa. But that's still too much work for many users because they need to learn a model in some offline tool and then hand translate to Vespa, which is burdensome, right? So we also support TensorFlow and any tool that outputs their models as ONNX directly on Vespa. So you can just save your TensorFlow trained model or model train in some tool that's compatible with ONNX directly into the application package in Vespa and deploy it, and Vespa will run it for you. Yeah. So this is kind of similar to things like TensorFlow serving, right? But TensorFlow serving is optimized for evaluating over a single data point, while Vespa is optimized for repeated execution of models or many data points for one query, which leads to different optimizations. So because of that, for the use cases we see, Vespa is faster even on a single node than things like TensorFlow serving. But the big difference is that we evaluate the models where the data is stored in parallel over multiple partitions, which means we can scale much better than that kind of solution because we don't run out of bandwidth to send the data somewhere to be evaluated. Yeah, I don't think I'll go into more detail. So we can catch up the time we have lost. So to wrap up, that's what Vespa is. If you want to learn more about it, go to vespa.ai, where you find all the documentation and so on, and pointer to the GitHub repo where we develop Vespa in the open. And feel free to send your commits if you have any. Yeah, if you want to try it out, you can run it on AVS or on your local Mac in a Docker container really quickly. We have quick starts for all that kind of thing. So really simple to try it out and get started. And if you have that you have use cases where it might fit in your own companies, please tip the right persons. Okay. Any questions? Yeah.
So you had compared Vespa to Elasticsearch, and the way that you described the architecture sounded a lot like the scatter-gather architecture of Elasticsearch. And you also mentioned that Vespa supports operators like join and reduce. Can Vespa create like arbitrary DAGs of operations like you would do in Tez or Spark to execute, multiple joins and reduces, which is something that is not possible in Elasticsearch?
No, you cannot do that on Vespa. I mean, you can write Java logic to do it on top, but not as native operations inside Vespa. And that's because things like a general join across all your data is just too expensive. There's no way to do that with this low latency. That is the kind of use cases that we support. So we have a sub case of join where the data you're joining with fits on a single node that we support in Vespa, but not general joins. The join you saw was within the Tensor language, which is where you have a single query and a single document and a single model. What is the actual thing you compute over just that data? And there you have a tensor math language, which includes join, but that's just a local data, right?